In this third module, we focus on the numerical aspect of vector field visualization. In particular, we look at integration techniques, and we focus on the numerical aspects because practically computation of implicit computation of, for example, streamline is not really possible in most of the cases, and in practical anyway. Still, having a high quality computation is very important in understanding the structure of the flow. For example, here in this case, you can see that there is a flow, a cell of the flow that goes up and down within this sequence of obstacles. And now an imprecise computation would probably let part of the flow escape into this rotational cell where the flow does not move forward anymore. So if one wants to have a precise understanding of how the flow evolves, having high quality computation of, for example, streamline is very important. In 3D, those are additional examples of computational streamlines, and where you can see how those are crucial to get a proper understanding of the structure of a flow. So, first of all, I would like to focus kind of more on the intuition on how things work. Let me uncover. So for this, I'm using a Mathematica notebook. You can find it on the web for the students in the class. I'll also attach the Mathematica notebook. And this is just a very simple example that allows to understand what we're going after. So here in this plot, you see kind of a few different functions that we want to approximate with numerical methods, and in a way get a sense for those different shapes, how the choice of a particular method influence and the type of integration basically influence the result and the precision that one can afford. So here there are Euler method, Runge-Kutta second order, and the coefficients, and the classical Runge-Kutta that would be the fourth order. And I'll just go and show a couple of variations on the approach. The idea would be that you take this interval that goes from A to B, so A is -3, you can see, let me mark it. So you go from coefficient A, that is the starting point -3, to B, that is the end point is 3 in the x-axis. And the number of steps, so in this case, to make the curve entirely smooth, I choose a very high number. And so here you see step size is 3 over 100. And then the starting value of the y coordinate, so along the y-axis. And so in this case, so you see, for example, that when I go from one curve to the other, so those, you see the different examples that we're going to work with. So let me clean up the top. And so now let's say the lowest kind of meaningful number, I would say, the lowest minimum number of steps it's 3. So here suddenly you see that you have 1, 2, 3 intervals along the x-axis. And so the simplest approach is the Euler approach. So here you see that with only 3 values plus the initial one, the approximation is very poor. So the blue is the original curve and the polyline is the approximation. But as we add more and more steps, the approximation improves. Still, you see that the points marked with this large circle, the large discs, do not lie on the curve, so this is still kind of a very poor approximation. And so we need to increase the number in a significant way before we get to an approximation that start to be reliable. If you go to the Runge-Kutta second order, you see now all the points lie on the same curve, so the approximation is fairly good. In fact, I can go back and reduce the number of intervals, which makes the method so improve even very, very few steps. So here, before, now you see the points start to depart from the actual curve, and so the approximation is now good and more. If we go to the Runge-Kutta higher order, so you see that now the approximation, so even if this is a linear component that seems to not approximate very well the shape, the extreme points are still effectively on the line, and so one can actually go and keep reducing the number of intervals, and only down to having only 4 intervals, the points start to be outside of the curve. So we can show similar results with different curves, just to get a sense. So here you see that, again, this stage of the curve is kind of the difficult part. You can see that here this point is happen to intersect the curve, but it's just by kind of almost giving the correct answer by mistake. Once the curve goes out of the original curve, the trajectory is not reliable anymore, right? This is way off. So yeah, even if at some point can reintersect and potentially recover the curve a little bit, clearly one cannot rely on that shape anymore. And so one will have to increase the number of steps quite a bit. You see, even now with like 20 steps, there is a fairly big separation. And again, it seems to recover only because the curve goes back and forth and kind of by mistake. But the reality, this could be start diverging more and more, so it's not really reliable. And so the number of steps that one would have to add is pretty high. So before the basic Euler method, again, this is kind of the simplest method to implement, give a reliable answer. So let me actually put 100 directly. And you see still in the king here, the curve is not well aligned and seems to recover again, not for good reasons. And so one would have to really go to a very large number of points to get a pretty good approximation. If one switch to a Runge-Kutta approximation, suddenly things improve in a significant way. For example, if I go back to 100 steps or 50 steps, I hope you're kind of following here what I'm doing with this selection. So if I go 50 steps, maybe 25, you see that the quality of the approximation keep staying fairly high, and before it will, and so even here, see the points stay on the blue curve still, and we're kind of down to, okay, now finally one of those points is getting out of the curve and kind of is having a significant error. But here we are up down to 6 elements instead of say 200. So I hope this can kind of give an initial intuition of what we're going after. So we're looking at how numerical computation can allow to compute trajectories of the curves, or in particular, say, the streamlines, in a way that is reliable. So we saw that kind of just as an animation. Let's look at the equation. So the first order Euler method has a fairly simple equation. So you have the position of, say you have a particular starting point, and we call this x of t minus dt, so it's kind of your previous location, and you want to compute the location that comes after that, so that would be x of t. So we increase x of dt by the vector at the initial location, so the vector here at the origin, so this direction, multiply by the amplitude of the step. And so from this point we get to the next. Now at the next step, this become x of t minus dt, and this is the new x of t, and so on. And so one can build this polyline by doing this simple addition kind of over time. Now, the method is not very accurate, but it's fast, and I would say also it's very simple. And as we saw in the animation before, there are higher order method, namely Runge-Kutta, that allow to have much higher accuracy with much fewer steps. So how the geometric interpretation work for this particular method, and how we kind of understand intuitively why one method is better than the other. And so when we have the starting value f of t minus dt, now the increment is the product of the variation in time, and so this direction, and this the value of the vector, and let's say this is, we have a one-dimensional vector, so the dimension in this side. Otherwise we do it basically component by component. So in a way, the area of this square is the amount we add to the initial value to go to the next one. So that's where it's kind of a very simple approach in terms of geometry of the computation. When we go to a higher order method, for example, the second order Runge-Kutta, so we start adopting a more complex formula that in a way is kind of a correction of what we would do with a simple Euler method. So x of t here, so initial point, is again adding the previous location, but now is the blending of two terms instead of a single one. So k1 and then k2, and average them together. And now k1 it's effectively the Euler term, but then we have this correction, so instead of only using this, we only use half of this, and then we have this correction term that sample the vector at the location and reduce the error by computing the vector v, right, at a location in between what would have been the first and the second location. So there is a sampling of this second vector here that builds a correction, so that we have this improvement of the computation of the vector field. Again, this is the explicit expression of the formula. So practically, this gives an improvement on the computation, and the geometric interpretation of this aspect is that then we have the computation of instead of the area of this entire rectangle, we eliminate this error term, and we have this kind of trapezoid, the area of this trapezoid, that is our term that we add. And notice that ideally we would have to do the integral under the curve here. But you see how that integral under the curve is much better approximated by this particular trapezoid. So to make things even better, that's where we go to the so-called standard method, which is really the fourth order Runge-Kutta, where, as usual, we do starting point is equal to the previous location, and now we have the blend of those four terms. They're also weighted, so this is 1 time, 2 time, 2 time, and 1 time. So adding them up is 6 really terms, so the multiplication to the middle ones. So that's why this is divided by 6, so they are averaged uniformly by weighting the middle ones in having a stronger influence. And so again, we have this sequence of terms where we sample the vectors along the line, and so you see vector of x t minus dt plus a certain term, and so on and so forth. Now, when we apply this type of formula, we have an even better approximation of the integral underneath this curve, and so you see how this is getting more and more accurate compared to the previous terms. Already the second order method does a pretty good job, but this is much higher quality, and especially when we talk about scientific data, that's why this approach is called the standard approach, is definitely something that give a kind of the minimum quality that you really want to use in practice. So let's look again at the practical use of those approaches. So here we look at, again, doing a numerical integration, and we look at an example that geometrically is very easy to interpret in terms of judging the quality of the result. So if the vector components x and y are, the x component is minus y, and the y component is x over 2, this field gives a settled concentric ellipsis. So any streamline here should be an ellipsis around the origin. And so if we start the integration in position 0, minus 1, so it's below the axis, so let's go farther down. So we can start evaluating the quality of the result. So this is again a sampling of the field itself, and now we can start thinking, okay, we start here at this particular initial point, and then we do a few steps of integration, and we start seeing how the trajectory is computed numerically. Here you see already how we would expect, being an ellipsis, that the distance from the origin at the top will be the same, and instead the computation already is off quite a bit, right? And as we keep moving forward and forward, so instead of wrapping around itself, the approach overshoot quite a bit. So now if we reduce the step, the delta t, and so in this case, for example, we did only 19 steps, and the delta t was too large, clearly. We can do twice as many steps with half of the delta t, and you see actually that the quality of the trajectory is improved in the sense that, yes, still overshoot, but by a smaller amount. So one can kind of compare the different approaches and see how they differ in terms of quality. In particular, that's the parameter that one can tune is the size of the step. And so here you can see that if you take a really, really small step, but then you have to do many, many steps, but the trajectory now at the end can converge to the proper curve, or at least be close enough that we cannot tell the difference visually. But with smaller steps, you see the trajectory diverge pretty dramatically. Already 10 times smaller, it kind of goes off, and so on and so forth. And so this is why the higher order methods are popular, because the Euler method, as soon as you start integrating also at a certain distance, the approximation is pretty substantial. So here we look at numerical comparisons. So if you do a delta t that is a half, and a quarter, a tenth, and 100, or 1,000th, so to reach equivalent locations, for example, do an entire orbit to compute the ellipses, you see how many numbers, so basically if it gets to the order of 10,000, but the error really goes down significantly, which is what one would want to accomplish. And of course, depending on the application, one could tolerate higher or lower error. Now, when we go to the Runge-Kutta second order, we have this new formula. We saw that this is kind of the general expression when you blend the two terms together, and that's what Heon's method is assuming that the two terms are a half, so this is an equal blending on those two terms. And as we saw, that already give a pretty significant improvement in the quality of the result. The fourth order, again, is much more complex in terms of the implementation of the expression, although now it's well known, and so it's really a question of typing those terms all together. But again, we know that now the quality is going to be significantly improved. So a quick comparison of sort of equivalent quality between second order and second order Runge-Kutta versus Euler, and we see that to achieve similar quality, basically every single step of the Runge-Kutta requires effectively 8 steps of the Euler. Now, to make a kind of an apple-to-apple comparison, or let's say 9 steps roughly, and so if we look at the complexity of the expression, if you look at the number of multiplications and addition in the Runge-Kutta, that does not justify using 8 or 9 steps in the Euler case. So overall, the cost of having the higher quality using the Euler method, it would be higher. So it's better to achieve the same quality. It's better to use the Runge-Kutta approach. And now one can go even higher, and look at the fourth order Runge-Kutta. So here you see the different trajectories, and you see that with a very low number of steps, the Runge-Kutta, the fourth order, quickly gets the proper trajectory, while the second order needs a little bit higher cost, and so here we go from 19, 38, and then the square of that, and so on, so that we have a clear balance that is in favor of the higher order methods to achieve higher quality in the data. So in conclusion, we have seen the main families of numerical integration used to computing streamlines and visualize vector fields, and in particular from the simplest Euler method, that could be considered kind of a quick and dirty approach to get a first impression over the data, versus a higher quality implementation using the Runge-Kutta approach at different orders, which single steps are higher cost, but overall they win in terms of the quality of the results that get computed, and so they're much more advised in terms of computation. Practically, though, it's important to report explicitly which method you're using so that the person looking at the data has a sense of how reliable the results are. As always, more than the precision per se, it's very important to communicate properly what is the quality of the results, otherwise the user can see a line and they don't know how reliable that line is. And thank you very much. This is all for the first section about vector fields, and next we'll continue